Okay, so nice to meet you. This is Maurizio Crozzoli, the work package 2 leader. I work in Telecom Italia team, and I'm going to present you the results of what we did in work package 2 within the RISE 6G project about use case analysis, KPIs, and the architecture proposal that we defined in our group for risk-based networks. Okay, so let's move on bit fast. Okay, let's start with scenarios and use case analysis. We are talking of risk-based solutions which implement the concept of environment as a service, where the risk can play different kind of roles. Essentially, they can let systems, services or performances being improved on one side, so you can talk of risk-aided, risk-assisted, risk-augmented, risk-based, risk-boosted, empowered, or enhanced, or you can deal with the systems where the risks let the services and performances be implemented. In this case, we talk about risk-enabled systems. Given this kind of names, of nomenclature, we can distinguish between 3 different kinds of scenarios and use cases. The first one is related to scenarios where the risk play a role in terms of enhancing, improving, enabling connectivity and reliability. Another kind of scenarios is the one related to localization and sensing. And the third area of investigation about scenarios and use cases is related to sustainability and security, enabled or enhanced by the presence of risk devices. As we will see, there are a number of use cases which can be selected in real life environments like the factory plant or the railway train station, which we dealt with in our project. About connectivity and reliability, as you can see, there are different situations, different scenarios. Some are related to the role of one single risk. Other scenarios have been studied where you have individually controlled multiple RISs. Other scenarios, again, deal with scenarios where you have multiple risks, not necessarily individually controlled. Then you can also have scenarios where there is a single multi-tenant risk situation to be investigated. And we also investigated scenarios where connectivity and reliability of the communication systems is enabled by the presence of mobile edge computing. I cannot go into details of all these scenarios. You can find all the details in our deliverables in the website, but I just showing you a list of all the scenarios and use cases we dealt with during our activity. About localization and sensing scenarios, we investigated 4 main areas. One is related to risks operated in reflection mode. Another one is where a situation where risk is operated in receive mode. Then you can have environments where risk is used in transmit mode. And in the end, you can also have risk operated in hybrid mode, with all the sub-cases that are shown here in the slide. About sustainability and security, we are referring to situations where you can get the best performances out of the communication system in terms of what is called EMF-EU, which is electromagnetic field exposure utility, or in terms of energy efficiency, or in terms of secrecy spectral efficiency, where with the help of the RIS technology, you can either enable or improve the performances in case of a single base station of multiple base stations. Then we described a large number of use cases you can deal with the help of the RIS technology in the factory plant environment. Here you can have a list and another list of different use cases can be described with reference to the railway train station environment, with a distinction in terms of different business model that can be applied to different use cases. Then I move to the topic of metrics and KPIs, which has been investigated within Work Package 2 as well, in a different task. We selected three main groups of metrics and KPIs. In the first group, we only selected the more traditional metrics and KPIs which are relevant to investigate the performance of risk-based systems. And you can see a list of these KPIs in the slide. But then we also selected what we can call beyond state-of-the-art relevant performance metrics, which are the EMF exposure utility and the secrecy spectral efficiency. The first one, the EMF exposure utility, is the data rate delivered to or transmitted by the intended user over the EMF exposure of the non-intended user or the intended user, depending on whether we are talking of the downlink or the uplink situation. About the secrecy spectral efficiency, it's defined as the difference between the intended UE RX rate and the non-intended UE RX rate. And the third group of metrics and KPIs refers to new concepts we defined in RISE-SG. The first one is what is called what we call the area of influence, which is the area of significant improvement of wireless connectivity enabled by the RIS. And the second concept is the band of influence, which is the frequency bandwidth in which any wave hitting the RIS gets reflected. Of course, RIS devices' role on spectrum coexistence between operators is an important part of our investigations. The last part of the presentation, which is very, very short, so I have to squeeze everything in very few minutes, is related to the network architecture proposal we defined within Work Package 2 with the help of all technical work packages, and also the deployment, some hints about the deployment strategies. Let's start with the network architecture. The starting point is the definition of 4 logical network nodes. The first one is what we call the RIS itself, the RIS device, which is based on, as George explained us before, with details, is based on reflector arrays or metamaterial technology. And it's something which is supposed to operate with a time granularity which goes up to 10 milliseconds. Then we have the RIS actuator, which is something which have to translate the logical commands received by the RIS controller and the RIS physical configurations. And it's intended to operate within 1 to 20 milliseconds. Then there is the RIS controller. The time granularity is higher. It's up to 100 milliseconds, and it's the component of the network which generates logical comments for the RIS actuator. And last but not least, we have the RIS orchestrator, which orchestrates multiple RIS controllers at a rate of a few seconds. In order to come to a network architecture proposal, we had to take into account the RIS characteristics in terms of hardware characteristics of the control channel, which could be either implicit or explicit. And then we also have to take into account the operation, the way RIS devices are operated. We can have both controlled RIS, where only part of the control is placed inside the RIS device itself, and we can have autonomous RIS devices where the whole control part is kept inside the IRS device. Then we have to take into account a number of requirements and recommendations. So we have selected a number of such requirements and recommendations. Among others, I would list here the dynamically changing RAS configuration, which should be able to operate at a sufficient update rate. We have to consider also the directional risk configurations with variable beam width, and where you have the main lobe whose directions should be precisely known.
So you have 1 minute left, please.
Yes, yes. Then you have the synchronization and also the different way of operating list devices, taking into account the data control flow and the control signaling. So given the few time I have available now, let me show what we have in terms of network architecture proposal, and which is shown here with its relevant interfaces between the architecture we defined and the ORAN 3GPP and ETSI network architecture. Let me only give you very last words about the challenging open issue of defining a common baseline which aligns all basic functionalities of different RIS technologies. And I thank you for being here today, and I close my presentation. Thank you all.